Thank you, everyone who's joined us so far. We are going to give people a minute or two to get in, and then we will get started. Okay, well, we've hit 100 people so far, so I'm going to go ahead and get started so we can maximize our time. Good morning or good afternoon, depending on where you're joining us from. And thank you for participating in today's Energy Communities Alliance webinar on reprocessing and recycling and the outlook and the impact for new nuclear development. I am Kara Colton. I'm the Director of Nuclear Policy for the Energy Communities Alliance, ECA, and I lead ECA's New Nuclear Initiative alongside Mayor Rebecca Casper of Idaho Falls, who serves as our chair. Under ECA's New Nuclear Initiative, which receives support from the Department of Energy's Office of Nuclear Energy, and also we coordinate with the American Nuclear Society, we are working to define the role of local governments in supporting the development of new nuclear technologies and to answer the three core questions. What do communities need to know to attract and support new nuclear development and missions? What and how should communities communicate to industry, national laboratories, state and federal governments about local resources and development opportunities? What hurdles and challenges will communities face, and who should we be working with to overcome them? To help do that, ECA has been hosting meetings and webinars to address these new nuclear technologies, federal, state, and developer priorities and timelines, regulatory requirements, workforce needs, and today, to better understand nuclear fuel reprocessing and recycling. Over the past year, DOE has amped up efforts to explore recycling spent nuclear fuel, awarding $38 million in funding last year for projects to develop technologies that advance used fuel recycling to reduce the volume of high-level waste requiring permanent disposal and to provide safe advanced reactor fuel stocks. Similarly, in Congress, there's been bipartisan support for exploring the potential for recycling, to establish a domestic industry to supply and enrich uranium, and to increase our energy independence. But this is not the first time the U.S. has considered reprocessing, and there have been multiple starts and stops. So what is the potential for closing the fuel cycle in the U.S., and how is the landscape different today? What will the impact be for advanced nuclear development, and what's the timeline? To help us better understand, I'm excited to introduce our two esteemed speakers. First, we'll hear from Paul Murray. Paul started his career working for the UK Military of Defense on the refit and design of nuclear attack submarines. After 7 years, he joined the UK's Atomic Energy Authority, working on recycling of advanced nuclear fuels, designing Gen 4 reactors, and the next generation of recycling plants. He supported British Nuclear Fuels on the design, build, and commissioning of the thermal oxide reprocessing plant and associated waste treatment facilities at Sellafield in the UK. In 1996, Paul moved to the US, working to support the transfer of technology from the UK to the US and on large-scale technology deployment projects at most of the DOE EM cleanup sites. 21 years later, Paul joined AREVA to support the Global Nuclear Energy Partnership, looking at building commercial recycling facilities in the US, working closely with multiple offices at the Department of Energy. ECA members were part of the multiple consortia that received grants under GNEP. We learned a lot from Paul there, as I know we will again today. This summer, Paul left his position at Orano, formerly AREVA, and is currently waiting to start a new position. After Paul, we will hear from Dr. Josh Durrell, Senior Technical Advisor to DOE on the Advanced Nuclear Fuel Availability Program, Nuclear Science and Technology Directorate. Over the past 5 years, Josh managed a pyrochemistry and molten salt systems department and a used fuel department at the Idaho National Laboratory. Prior to arriving at INL, Josh was for 7 years at the Oak Ridge National Laboratory with a focus on modeling and simulation of nuclear reactors, as well as spent fuel management. We're going to let Paul and Josh present their prepared remarks, and then we will be opening the discussion for your Q&A. I'll let you know when that moment starts, and we will ask you to submit your questions via the Q&A button. So with that, let's get started. Thank you all for being here, and Paul, over to you.
Oh, perfect. So everyone hear me okay? Perfect. So once again, I want to stress I am not affiliated with anybody. So these are my personal remarks. Cara actually saw me talk at the Nuclear Forum in Nebraska a few weeks ago and asked me to give the same presentation again today. So that's what I'm doing. I want to stress that the presentation is really not proposing reprocessing. It's not against reprocessing. It's just trying to lay out the facts for reprocessing or recycling in the US. I also want to say, since coming to the US in 1996, I have worked at most of the DOE sites, worked very closely with ECA and a lot of the local communities at the site. I've had the pleasure of supporting projects with ECA and the communities. Of particular note, I'd like to remind everybody about the Energy Park Initiative, where as Areva at the time and the utilities, we try to build some commercial reactors up at Portsmouth. So reprocessing. So briefing on reprocessing. So as Cara mentioned, there's been a lot of starts and stops in the past. We got Barnwell down in South Carolina. We had ICPP out of Idaho, basically down blending with Navy fuel for reuse. For West Valley, G. Morris, H. Canyon. And I've purposely left out the facilities at Hanford. But so you can see that it's been tried a lot in the past here. So next slide, please. So what's the difference? Some people say reprocessing, some people say recycling. So let's talk about what the difference is. So spent nuclear fuel is defined by NRC as having no use, send it to a repository. Where you draw the line between being useful and not useful is quite arbitrary. Used nuclear fuel is suitable for reprocessing, recycling, or disposal. Yeah. So reprocessing is when you take the used nuclear fuel and you basically separate it into waste and potentially useful products. And this is what the UK did. Right? Recycling is when you take the useful, you basically do the same thing, you reprocess, but then you take the useful products and you basically turn it into new fuel, which goes back into a reactor. At the moment, all the commercial facilities in the world use the Purex process, and the Purex process was invented here in the US. Okay, next slide, please. So this is where this slide is. I want to show one particular thing on this slide. This is the location of all the operational US reactors. NRC divides the country into 4 regions. Okay? That's the big point I'm trying to get across. 4 regions in the US where all the reactors are located. Next slide, please. This is where the used nuclear fuel is by state. So you can see this was taken from 2022. So the number is closer to 90,000 tons of used nuclear fuel. So we have a lot of used fuel in the US, and nobody's proposing and nobody can credibly say that they can reprocess all this used nuclear fuel, plus the new fuel that is arising each year. Okay, next slide, please. Not all fuel is equal. So the fuel that comes out of a reactor, depending on how long it's been in the reactor, has a different burn up. So how much energy, useful energy is actually being produced by that fuel. In the early days of nuclear power, the burn-ups were quite low. Now we're pushing to higher and higher burn-ups. The higher the burn-up, the more uranium has been converted to minor actinides and fission products, so you produce more waste. So from a processing recycling point of view, you would like to get the younger fuel with the lower burn-up because it has less waste products. But all fuel could be reprocessed or recycled. Okay, next slide, please. as we talk about reprocessing, recycling, we can't forget that at the end of the day, no matter what we do need the geological repository. Better or worse, we picked Yucca Mountain in Nevada, designed to take 62,500 tons of used nuclear fuel. Next slide, please. The drifts were built, the tunnels were dug, the facility was, getting ready to go, and it was stopped by an act of Congress. Okay, well, not an act of Congress, but it was stopped because it lost political support for the mountain. Long projects are subject to the potential to be stopped politically. Okay, next slide, please. Having said that, fuel is going to be moved by rail. It's going to be transported by rail to Yucca Mountain, where it's going to be unloaded and then placed into the drifts. Next slide. So once it was in, one very important thing about Yucca Mountain was it was not only going to take the used fuel, it was also going to take DOE waste as well. So all the high-level waste that Savannah River is producing, the thousands of vitrified canisters of waste being produced there, thousands of canisters being produced by Hanford, were all going to be shipped to Yucca Mountain by rail and be stored in the mountain. Okay, next slide, please. Existing reprocessing plants in the world. France has the Le Havre facility, two lines, two facilities with a throughput of about 1,700 tons a year. And they have reprocessed not only light water reactor fuel, they have reprocessed advanced fuel at the site as well. The thermal oxide reprocessing plant at Sellafield shut down now. It had a nameplate throughput of about 900 tons a year. All reprocessing for advanced fuel in the UK was primarily done at Dounreay in Scotland, where they had a dedicated line operating to support the fast reactors. The Kashimura in Japan drew on the designs from both Le Havre and Sellafield. It's going to be at 800 tons a year when it finally becomes operational, and it hasn't reprocessed anything yet, so it hasn't done any advanced fuel. The Russians have Mayak, and they've reprocessed advanced fuel, building 205 at Sellafield. That was shut down in the last few years, had a 1,500 ton a year throughput, and reprocessed advanced fuels. And India has about a 275 ton a year facility, and China also has a small facility as well. So commercial facilities do exist and have been running for a considerable length of time, and some of them have run through to the end of their lives. Okay, next slide, please. So this is Sellafield in the UK. So this does everything that Savannah River and Hanford does, but on a mile by a mile site. You can see the North Sea off to the left. The site was originally set up to recover material for the weapons program and was then transitioned over to commercial reprocessing. So a lot of the horror stories that you hear about the Sellafield site were really associated with the weapons program as opposed to the commercial recycling. Next slide, please. And this is the thermal oxide reprocessing plant. This is a state-of-the-art plant built by the UK. It's a beautiful facility. If you ever get the chance to visit, you should visit. All the main process cells had big windows in, so you could see the operations. So you could see used fuel being moved into the shearing cave. You could see the dissolvers. Everything was set up to basically showcase and show people what was happening in the plant. Okay, next slide. So why did the UK reprocess? It's really simple. 50 plus years ago, the UK is basically a lump of coal sitting in the Atlantic. They are worried that coal is going to run out. They've then become dependent on foreign supply. They needed energy independence, so they started a program for Generation 4 sodium reactors with reprocessing, with the aim to breed and burn plutonium. Dounreay fast reactor was built. The prototype fast reactor was built and operational. The European fast reactor design was started in a consortium with Germany and France. And the idea was that the UK was going to basically transition to a fleet of sodium reactors and basically become energy independent from the rest of the world. Right? And so all the plutonium which was separated was ultimately destined to be used in sodium fast reactors. So the UK reprocessed, separated plutonium, and generation 4 reactors were never built. Okay, next slide, please. So why did France recycle? France, one of the big drivers for France was to reduce the size of the geological repository. France has 56 operational reactors. They didn't reprocess. The size of a repository would be about 5.4 square miles in area. If they reprocessed and disposed of the high-level waste and spent MOX, that size would reduce to about 3.5 square miles. So they get a 35% reduction in the size of the repository. So instead of spending money to build a big repository, they basically taken that money, invested it in reprocessing, and closed the fuel cycle that way. France was also preparing for a fleet of sodium fast reactors as well. Okay, next slide. So this is a used fuel assembly, and I'm assuming everybody on the call knows what a fuel assembly is. So it's uranium-235 enriched to about 5% when it goes in. When it comes out of the reactor at the end of the life, and a typical burner between then about, well, these numbers are based on about 40 to 45 gigawatt days per ton burn up. You get 1% of that uranium's converted to plutonium. You still have 95% plutonium uranium at much lower enrichment. Then you have about 4% minor actinides and fission products that you really can't do anything with. And then you have all the metal structure, which is high level waste, which you have to treat and dispose of. Okay, next slide. So this is the first process in France. So in France, they don't store the used fuel at the reactor sites. The fuel is, as quickly as possible, put into shipping canisters and moved up to the Le Hague site. So the canister arrives at Le Hague. It is basically, it arrives horizontally, it's turned into the vertical position. It's made it up to a hot cell. The cask is opened, and then the fuel assembly is removed. It's quenched because the fuel assembly is still thermally quite hot, and then it's put into a basket. Okay, next slide, please. And then the basket is moved into one of 4 storage pools at Le Hague. So Le Hague currently has the capacity to store 30,000 tons of used fuel in fuel pools at the site. Okay. Next slide, please. So when you're ready to reprocess the fuel, the basket's moved over to the right location. The fuel assembly is moved up into what's called the shearing cave. It moves over, it's basically gripped very hard and then crushed a little bit, and then a large shearing blade basically comes across and chops the fuel assembly into segments about 1.5 inches long. The big metal end pieces at either end of the fuel assembly are chopped off at the beginning and the end and are sent off for treatment. Next slide, please. So these shared fuel segments in the French system fall into what's called a continuous dissolver, and this is like a large paddle wheel with buckets. And so the fuel, basically shared fuel, falls into a bucket. The bucket contains nitric acid. The nitric acid dissolves everything apart from the metal. The metal parts, when all the fuel is dissolved, the metal parts are basically washed and sent off for treatment. And then all the dissolved product is then sent off to the separations part of the plant. Okay, next slide, please. So this is the simple mass flow. So if you put, for every 8 new fuel assemblies you put into a reactor, you hopefully get 8 out. The 8 used fuel assemblies then go into a recycling plant. You get enough uranium that you can re-enrich it to produce 1 re-enriched uranium assembly, and enough plutonium to make 1 MOX assembly. You can then put those MOX assemblies and reprocessed uranium assembly back into a reactor, burn it again, and then you get used MOX, used reprocessed uranium. And at the moment, there's no way to reprocess that material. There's work ongoing to demonstrate it's feasible, but at the moment, nobody reprocessed uranium fuel assemblies or MOX assemblies. Okay. Next slide, please. So, as Carl mentioned, a lot of the ECA or the ECA communities are considering interim storage. So this is what an interim storage facility would look like. It's basically a rail spur, an unloading facility, and a cask storage facility. Next slide, please. So what's the economic impact to a state or a community for actually hosting this type of facility? EPRI and the utilities actually produced a report that looked at what it would take, the cost of building a 40,000 ton interim storage facility in the US. We took that report and the numbers in that report and we gave it to the University of South Carolina Business School, the Dames of Moore Business School. They took the numbers and they have a model, an economic impact model, which they use to run for Boeing, for BMW, anybody that wants to site a big commercial facility in the US. If they put the numbers in, they ran it to show what the impact would be to a state or a community for interim storage. They did neglect to include any incentives the host community would get, but the basic numbers were, can get the next slide, please. So to actually build a facility to host 40,000 tons of used nuclear fuel requires just over 200 people. To operate it, it requires less than 150 people. The annual economic impact to the state or the community during construction is just less than $30 million a year. And the annual economic output from that facility is just less than $15 million a year annually. Yeah. The numbers are probably dated, but it gives you an idea of the scale of impact for hosting 40,000 tons of used nuclear fuel. Next slide, please. So one of the things that you've got to consider is, okay, for the long-term storage of fuel, we need some form of R&D facility to support, to show that it's safe. One of the things that's been talked about is, could you build a dry unloading facility? So just like the French head ends, where they can take a cask in, they can open it dry, they can take fuel assemblies out, put fuel assemblies back in. You could build an unloading facility to allow you to access the fuel, some hot cells to basically look at those used fuel facilities. You could have an accelerated aging pad like they do at Idaho, and you could have computational fluid facilities like you do in Idaho and universities and stuff. Okay, next slide, please. One of the other things that you need to consider is that in the UK, now Thorpe's finished its mission, the NDA has decided that they are going to use the Thorpe pool as a way to store all their used fuel that they own. So all the NDA fuel is moving to Thorpe to be stored in the pool. Next slide, please. France, the EDF in France, the large utility, is building a pool and an unloading facility, a centralized storage facility to basically store the used MOX and used REPU, which will arise in France. This facility is designed to hold 10,000 tons of fuel, about 21,000 fuel assemblies, and the cost of that facility is $1.4 billion. Next slide, please. Sweden's taken it one step further. They've built and designed a storage facility to store 8,000 tons of fuel. This facility has been built nearly 100 feet below grade. So no longer building just surface facilities, you're building a facility below grade to basically store your used fuel. Right? It costs more, but it's more acceptable to the people to do it this way. Okay. Next slide, please. So this is the slide that's taken from the GNEP studies, and we've presented it. It's been presented many times. We've presented it at the Nebraska Forum. In the top right corner is the dry unloading, cask storage. You have the dry unloading facility. The big yellow arrow is pointed at what would be the separations facility. Okay, so that's where all the material is removed from the fuel. You hear some people talking about how small their facilities are. Everybody needs everything else at this site. The separations facility can be whatever the separations facility is, but you still need ways to treat your high level waste, your secondary waste. You need maintenance facilities. You need office blocks for your staff. You need a canteen. You need a car park. So everything else stays the same around the facility. What's in the building in the yellow arrow is entirely up to you to build whatever reprocessing scheme you want to do. Okay. Next slide, please. So one of the things we talked about is an initial recycling facility. What would be the right size to potentially build in the US? So we proposed an initial facility of about 800 tons using the best available technology. Why pick 800 tons? Because over the entire lifetime, 50 to 60 years, the reprocessing plant could take all the used fuel in any one of those 4 NRC regions and reprocess it all. You're not trying to address all the fuel, you're just addressing the fuel in a region. Remember, it's impossible to reprocess all the fuel. The process would recommend would have no separated plutonium, and you'd manage the product using the existing light water reactors while you're waiting for generation 4 reactors to come along. Okay. Next slide, please. So the numbers for this were done during GNEP. The numbers were audited by DOE several times. The numbers were provided to the University of South Carolina. They put it into their model. This is the number of jobs that are actually required to build a recycling facility. The number of jobs peaks at just under 18,000 people directly employed on the site. Remember, this is just a pilot plant in one region. The secondary jobs were about 2.6. So for every primary job, you had 2.6 secondary jobs directly supporting the facility. The economic impact to the state and the region was measured in percentage points, so it is quite significant. And then once the plant was operational, you had 4,000 to 5,000 people, high-paid staff working in that facility for the next 60 years. That report, that presentation was done to the Nuclear Infrastructure Council and is a public document. And I'd encourage the ECA members to basically try and get hold of a copy of that presentation, and they can see all the numbers. It was broken down. It considered every single, the model was run for all 4 regions of the US. Okay. Next slide, and then I'll try and shut up. So potential sequence could be outreach to host communities, some form of consent-based siting process, build the technology evaluation center, move some fuel to the TEC to examine the fuel and how it would behave, demonstrate that some of this used fuel could be repackaged into smaller transport and disposal systems. I strongly recommend for host communities look to establish off-ramps, then start to build your pilot facility, starting with interim storage. Then you can look at direct disposal, pilot recycling, or something else. Okay, next slide. So in conclusion, recycling and reprocessing is technically feasible. There has to be a strong driver to implement reprocessing and recycling. Safeguards of special nuclear materials can be managed. The schedule for building even a pilot facility is measured in decades. And you definitely need an end user for the product fuel. And with that, I'd like to hand it over to Dr. Jarrell to continue the discussion.
Great. Thanks, Paul. Let's see here. I'll wait for my slides to get up. In the meantime, let me just sort of introduce myself again. I'm Josh Jarrell. I'm an INL employee. However, I've been on detail to the Department of Energy for the last year, supporting securing nuclear fuel for advanced reactors. So I'm going to sort of take the discussion a little bit differently and focus more on advanced reactors, how the fuel supply is impacted for those reactors, and how does recycling potentially come into play. And hopefully that'll cover the gambit before we open it up for questions. So next slide, please. So when we start talking about recycling, I always like to think about how important it is to not just reprocess the fuel, as Paul mentioned, but to actually recycle and make it usable. And that's especially important for advanced reactors. It's not just recovering the uranium and plutonium and valuable material there. You've got to have the ability to fabricate the fuel, and there's different challenges with recycled material, and you have to have the reactors ready to go to actually use that fuel to produce power or other needs. And so it's really important to consider the whole life of this material and how it fits into play. And then I'll just note one thing that is always very important when we do research around recycling or nuclear material in general is ensuring that we minimize proliferation risk for all these processes. These are potentially new processes. And so we want to make sure we're very cognizant of safeguards and how do we deploy fuel cycles that we can properly monitor. And so some of the investment that the department has done over the years has been on improved sort of proliferation models and non-proliferation and security by design for these sort of new concepts. So let me dive in though to the advanced reactors. Next slide. So these advanced reactors are very different potentially than our current fleet that we've deployed here in the U.S. Our current fleet is, as Paul mentioned, were these light water reactors. There are a couple different types of light water reactors, but generally they were all light water reactors. And the main differences between the next generation, what we're calling advanced reactors, and the current fleet is the next generation could be potentially smaller sizes. They could be built and constructed with less capital cost. It could be ran more effectively and efficiently. It could be used for more than just electricity, more reliable, and just sort of advancing the technology and utilizing that. One of the main ways that they're different actually is the fuel itself. So most of our light water reactors use enriched uranium to 5%. A lot of these advanced reactors are looking at the uranium enrichment up to 20%. And that actually provides a lot of opportunities when it comes to the fuel cycle, but also a lot of challenges to get that fuel initially supplied to actually deploy some of these reactors. Go to the next slide. So this slide really just sort of outlines that there's a lot of different concepts out there for advanced reactors. And our current fleet or light water reactor, they use oxide fuels, again, 5% enriched. And there are some concepts that are small modular reactors, essentially just smaller systems, which based on our current light water reactor fleet, with some I'd say better safety features. However, I think when we really start talking about advanced reactors, there's a lot of different fuel forms, and I'll just sort of highlight them here. You have TRISO fuel, which are particulate fuel, where you can use generally it's a thermal reactor with fuel in particulate form. You have metal reactor or metal fueled reactors, so you have the fuel that's in a metal form. Those actually have a lot of opportunities if you can use actually fast reactors. So that the term fast or thermal relates to how fast the neutrons are moving in the reactor. But the fast reactors are actually much more accommodating of different fuel forms. So you maybe don't need just uranium. They might be much more accepting of other materials in the fuel. And there's a handful of other fuels that are being considered for some of these designs. One thing I just say is there are a lot of different concepts on the table right now. The federal government has been supporting advanced reactors pretty significantly. But until we sort of see who gets over the finish line, it's sort of hard to predict where to do significant investments in the fuel cycle. So a lot of these things, I'll sort of identify some of the challenges, but we still, until we sort of see how these advanced reactors are deployed, there's still a lot of uncertainty around the fuel cycle itself. Next slide. Here, I just wanted to be a little bit more specific about the reactors that are being considered right now and that have either received DOE or other support. We have two big reactors. The DOE program, the Advanced Reactor Demonstration Program, has two demonstration reactors. One is the TerraPower's Natrium reactor, which we hope to deploy in Wyoming. The other is the X-Energy XE100 reactor, which we hope to deploy down with Dow Chemical in Texas. But there are several other reactors, Kairos, Westinghouse, BWXT, Southern, Holtec, that are being considered, and DOE is actively funding to support deploying those reactors. In addition to the DOE funded ones, there's also DOD funded project to develop and deploy a transportable reactor. There's also several, and this is not a complete list, of privately funded advanced reactor companies that are very interested in deploying advanced reactors. The vast majority of these needs this higher enriched, which is high assay, low enriched uranium, HALEU, you'll hear that term, fuel to deploy. And so one of the big challenges right now is finding HALEU to actually help these advanced reactors deploy in the next several years. So if you go to the next slide. So as it relates to HALEU, we don't have a commercial supply of HALEU right now in this country. With fuel, you really have two options to produce fuel for these reactors. One is what I'll call the standard commercial system, where you actually mine uranium from the ground, you then enrich it, and then convert it to fuel that's then able to be used in our fleet of reactors. Unfortunately, we do not have those capabilities readily available for HALEU in this country right now. We can stand up those facilities. They're going to be new and sort of different facilities, but right now they don't exist. And because of that, it's going to be several years before those capabilities come online. And so in the meantime, in the next 2 or 3 years, when we want to see some of these advanced reactors deploy, we need to find fuel to support those things. And so the way that we're doing it is actually a recycling technique where we're recovering highly enriched uranium. So the current light water reactor is 5%. These advanced reactors maybe 20%. So highly enriched is much higher than that. We can recover that material and then mix it with some lower enriched material to get to that 20% enrichment range. And so DOE is actively doing that as a means, so we'll call it bridge the gap until these sort of larger scale commercial HALEU supplies come online. So next slide. So let me specifically go into the recycling aspect of this, since I think this is sort of the intent. We are actively recovering material and downblending it to make HALEU. This is conceptually a simple process, but when you actually get into the details, you need the right form of the material. Some of the material was in spent fuel, and so it can be a challenge to reprocess it and get it back. And then you need to make sure that the fuel that comes out, again, is useful for the advanced reactors. As I noted earlier, it's not enough to just recover it. You need to make sure that you can use that material in future fabrication, and then that material is actually useful in these reactors. So DOE does have two main active sort of recycling efforts that are being funded. One is recovering material at INL from the experimental breeder reactor, and I'll dive into a few details on that in a second. The other is recovering fuel at the Savannah River site and downblending it. Both between the two, there's probably 12 to 13 metric tons of HALEU that could be made available through those programs. In addition, DOE is very interested in working with NNSA and other programs to see if there's excess material that could be used for advanced reactor fuel. So they have identified on the order of about 5 metric tons worth of material that could potentially be used from those stockpiles. You go to the next slide. So I want to just specifically call out recycling that's active and DOE is supporting. This is the EBR2 processing that's going on at the Idaho National Laboratory. We actually use a pyroprocessing reprocessing technique. This is actually a little different than the Purex process that Paul mentioned that's been deployed at commercial scale. This is a batch process where you're able to recover the uranium in what we call large ingot form. It's these very large metal pucks. We then are able to recast and melt that material down. When we're doing that, we're able to reduce and remove a lot of the contaminants that make fuel fabrication and future beneficial use challenging. And now we're at the point where we have these very small, they're actually Dixie cup sized metal pieces of HALEU that can be used for fabrication, specifically for metal fueled advanced reactors that are using fast spectrum. Having said that, as I mentioned earlier, there's lots of fuel and reactor concepts that don't need metal. They want to make TRISO fuel, and to make TRISO, you really need oxide to make that material. And so we have just kicked off an effort at INL to basically polish that material, so further reduce some of the contaminants and clean up the material and convert it to an oxide so that it could be more widely accepted for use at other advanced reactor companies. Next slide. And so I'll end with this, and hopefully this will seed some conversation. With these advanced reactors and the fact that they're using this higher enriched fuel, there's more value in the fuel as it comes out. There are lots of scenarios where you can recover the uranium and actually downblend it for use in other lower enriched reactors. There's scenarios where you could potentially re-enrich it back to the levels it was. And then also with the advanced reactors, a lot of them can use things other than uranium, specifically plutonium or different uranium isotopes than they're normally used to power those reactors. And so because of that, there's a lot of opportunity associated with recycling in the advanced reactors. So we need to fuel the first ones, but as we start deploying them, there's going to be several opportunities to use that recovered material. Now, I will say again, there are challenges associated with this recovered material, mainly due to the material is not, I'll call it clean, fresh uranium. It has different uranium isotopes than you would normally get. And because of that, there's challenges both on the fabrication of the fuel, if you're going to use that uranium, as well as in reactor performance. And you got to make sure that the fuel that you're using in these advanced reactors, you have a good handle on what the material really is and the isotopes there to make sure you can run these reactors more effectively. And so I'll just end with the department, because of those challenges and the potential opportunities, has been funding recycling research around uranium recycling for several years and will continue to do so. So with that, I still think I've left some time for questions.
Great. Thank you so much, Paul and Josh. Really appreciate that information. I guess just one question to kick off the Q&A. And again, I encourage everybody to add their questions using the Q&A button down below. So when we're talking about reprocessing and recycling, what is the ultimate waste product that is produced that will have to go where? To a repository itself? Or are there going to be other disposal pathways for the waste products produced by recycling and reprocessing? And then one question just to add to that is, how many times can used fuel be reprocessed and recycled?
Okay. So the ultimate waste streams, primary waste streams, of course, is for high-level waste. And the high-level waste is vitrified waste and the compacted, metal products from the fuel. They're put into what's called the universal canister, which is probably about a third the size of a DOE standard canister. And you get about, it depends on the fuel burner, but you typically get about 2 to 2.5 standard canisters of high-level waste products from vitrifying about 1.5 fuel assemblies. The secondary waste, once again, depends on where you build the facility, but there's some very good reports done and presented at Waste Management by Ariva. They give in great detail all the secondary waste that would be produced in the US from an 800 ton a year plant. So if people are really interested, I would Google Ariva Waste Management waste from a reprocessing plant, and it's a very, very detailed report. Okay. Can you keep recycling used nuclear fuel? So when I worked for UK AEA at Dounreay in Scotland, we were reprocessing fuel coming out of a fast reactor. So we were doing multiple recycle of fuel through the reactor. Every time you recycle, though, we recovered for plutonium and uranium, but we did produce waste products that had to be vitrified. And for some reason, we did find that it became harder and harder to actually dissolve the plutonium the more cycles it had been through the reactor. But in theory, you can keep going. In practice, it became challenging.
Thanks, Paul. Josh, do you have anything to add?
Yeah, I mean, I'll just echo what Paul said. I think, you know, as far as how long you can recycle, again, it depends on the reactors and the facilities that you have to recover the material. There are conceptually reactors that could, you know, almost do, you know, can just keep recycling this stuff. Maybe you have to add some material along the way. But there's no real limitation there, but it's really an operational how you actually can recover it. One thing I'll note on the other piece, on the high level waste. So you do in recycling, you get these high level waste canisters, think glass and canisters, and that does need to be disposed of in some sort of deep repository. You potentially could use, you know, boreholes as a concept, but again, it is high level waste. It's radioactive, and so you do need a repository of some sort, regardless if you do recycling forever. So that's one point I just want to reemphasize is it's not a panacea that you don't have waste anymore. There's all, and the other piece is you generate every time you do reprocessing other secondary waste that have to be managed. Maybe they're not as challenging to manage, but there may be more volume, for example. So it's a trade-off for these facilities.
Great, thank you. I'm going to start taking questions from our audience. First question is, why is it only a 35% reduction in repository size if the light water reactor spent nuclear fuel and mock spent nuclear fuel can be recycled?
Because remember, every time we reprocess, it's those numbers were taken directly from the ANDRA, which is the French people in charge of a repository in France. So I would refer if the person, is it Carl, wants to email me afterwards, I can get him to the link to look at all the different options that Andrea looked at. I think they just recently updated their numbers, but it's still, that's the type of number you're looking at, 35% reduction. I think it was something to do with the heat load, where the used MOX was a lot hotter than just normal uranium fuel, and so that reduced the number of packages. But I could be wrong. If you want to give my email address out, I'll gladly get the link to that, Cara.
Great, thank you. Appreciate it.
Yeah. Can I just weigh in there just real quick? I think any of the analysis, when you look at a repository performance compared to a once through or a closed cycle or an open cycle, it's going to be very dependent on the repository itself. As Paul mentioned, the environment may really drive, you know, the thermal heat load may require more spacing, and you have more, you know, area. The isotopics, what are the engineering barriers? There's a whole lot of really challenging science that goes into repository design. And so I think it's probably sort of naive just to say, well, on a rule of thumb, it's 35%. I think if you did the analysis in a different geology, you'd probably come up with a different answer.
Yeah.
Great, thank you. We have a number of questions, as maybe you all can see too, about the economic viability of reprocessing, which, you know, we know in the past were reasons that it didn't move forward, both in the UK and in the US. So what's changed today to make this conversation as a priority discussion. How does the economic benefit work today? What does this do for the outlook for advanced nuclear development?
So in my experience over the many decades I've been involved with this, I've seen it many times. People can argue that it's economically viable, it's too cost prohibitive. So you can make the numbers come out wherever you want them to come out, depending on where you draw the boundary. To answer the question specifically about Thorpe, so I was involved with Thorpe, and so Thorpe was actually, a large part of Thorpe was paid for upfront by the customers. Okay, the facility had a design life, the set design life, and so it worked off the fuel for its customers, and it was making, at the end of its life, it was making the NDA a lot of money each year, and they're using that money to offset decommissioning costs at Sellafield, and that profit they were making should be public information, and it was measured in hundreds of millions of pounds a year they were generating in income. The problem was the facility was designed for a set life. I believe it was an evaporator C that went bad and had to be replaced at a cost of over £1 billion. Okay, and so the decision was taken that the facilities at the end of life, it was not worth pursuing additional contracts because the risk of another major failure on the plant would wipe out any commercial profits that facility would make. And so that's the biggest driver for shutting down that facility. But all the profit numbers should be publicly available from the NDA.
Thank you.
Okay.
All right. I'm going to move on to a question from Kenya Stump from Kentucky. Are there emission regulatory limits that prevent moving forward with reprocessing in the United States? She recalls concerns over xenon and krypton air emissions when she was touring PNML. Yes.
So there's an EPA regulation 40 CFR 190 that regulates the fission gases released from a reprocessing plant. And it's probably the biggest technical hurdle to reprocessing in the US. And it covers the entire uranium fuel cycle. So it's for mining, everything, mining, use in the reactor, dry storage and reprocessing, and the repository. So you can't go back and try and check, you can't go back and try and reduce that requirement. So it's something that would have to be addressed. There are potentially technical ways around it. You know, are they financially viable? I think time will tell. But it is probably the major technical issue for reprocessing in the US.
Thanks. Josh, did you have anything to add?
No,
All right.
I think Paul got it.
Great. Here's one that's kind of taking us a slightly different route. Can you describe the production of valuable isotopes, such as for medical uses, that can be extracted during reprocessing? And can those generate revenue to bring down total costs?
So there's not an easy answer to this. So every time, so you build a race car and you want to go racing with it, but then you want to use it to go and collect groceries and stuff like that. So now you're adding on complexity to your race car. The reprocessing plant would be designed to reprocess commercial use nuclear fuel. If you start to add on additional requirements for that facility, then you start to add on complexity to the plant, additional costs, additional maintenance costs. You could potentially, so in a typical reprocessing plant, it's something like 30,000 samples are taken each year. You could potentially harvest some isotopes from those samples. So you're not affecting the main process plant. You're basically harvesting medical isotopes from the samples you take. The more complexity you add to the plant, the more costs, the more issues you start to have. Okay. So the answer is yes, but type thing. Okay.
Yeah, and I'll echo that. There's a lot of nuance when you start looking for specific isotopes you want to recover. And so You need to be intentional on that to begin with, if that's something you really want to do. Adding on after the fact to try to get one or two things can be very challenging, and from a technical and economic perspective, it may not make any sense. I do, again, I think there is the potential with new fuel cycles and advanced reactors that, depending on the yield of a specific isotope that you might be interested in, you could potentially do that. But it really would have to be very intentional.
Thank you. A question for you, Josh, also. Are any of the DOE spent fuel, I think they mean the nuclear waste fund, being allocated to help with recycling, and could they be?
Okay, so I'm an INL employee and I'm not a lawyer nor a Fed. So I got to be really careful here. I think generally the nuclear waste fund is focused on disposal only. And I do not believe their funds have been used for the funds are not currently used for recycling work in the, historically I can't speak to that. But yeah, that would surprise me a bit.
Okay, thank you. Another question. I guess I don't need to keep saying that since we're in the Q&A portion of this call, but I apologize. Is there anywhere where infrastructure already exists so that we could start with reprocessing without having to start at square one? And either one of you.
So Paul's first slide had pictures of our reprocessing capabilities, both commercial and then some of our, I'd say, national lab, U.S. complex ones. It depends what you wanted to do on if they could be restarted or you'd be starting from scratch. I know, Paul, what are your thoughts?
So remember, I am not affiliated with anybody. Okay, not affiliated with anybody. But my personal opinion is that in the US, reprocessing was started 50 plus years ago for a very specific reason, right? To recover as much plutonium as possible to support the future generation 4 reactors. So we got separation efficiencies of 99.999%. I would challenge today, do we need such high efficiency? What are we going to do with all that plutonium? So why go back and, design something and build something that our grandfathers designed and built? And I'm probably talking about my grandfather, as opposed to a lot of people here. But why would we do that? Why wouldn't we, as the US, come up with a separations approach that we wanted to do? What happens if we only recovered 40% of the plutonium, sent everything else to the waste? Why would we do what's been done before? Does it make it cheaper, simpler, quicker to build? Could we leverage existing vitrification facilities? I think there's a number of options that could be done. So,
thanks. I think we have time for this one last question. Will different reprocessing and recycling facilities be needed for each type of fuel that advanced nuclear reactors are going to use?
I'm going to let Josh answer that one.
Well, I would say it depends on the technique that you use. I would say you don't have to have a completely separate facility for each type of fuel. You probably are going to have to do some pre-processing, some head-end activities to get them in a form. Depending on the recycling technique that you select. I think Paul mentioned you can do different separations recycling with different fuels, and the UK and others have done that. But I would say every fuel has its own challenges, and you want to get really good at reprocessing the fuel that you're focused on. And so that's why if you look at, the French model, their fuel that they're reprocessing looks really similar, almost every stick coming in. There's a reason for that, in both economically and what the facility looks like.
Great. Paul, do you have anything you want to add?
No, I've tried to reprocess most types of fast reactor fuel. So Josh is right. It all depends on your head end and then most of the rest stays the same. So,
Well, let me bring us to a close as we're just at the tail end here. And thank you so much to Josh and to Paul for taking the time to put together the presentations and explain these issues to us. I also want to thank the Office of Nuclear Energy at DOE and ANS for helping us make sure that this was pulled together well. And I want to thank everybody for joining. We are doing more webinars, and I just want to give everybody a heads up that our next one is going to be on Tuesday, October 31st. That is Halloween, where we're going to have a webinar looking at Clean Up to Clean Energy, how to develop a project on federal lands. We'll be joined by Candace Robertson, the Senior Policy Advisor for DOE's Office of Environmental Management, and ECA